The reaction rate constant. The reaction rate constant K is not truly a constant. It is merely independent of the concentration of the species involved in the reaction. It is almost always strongly dependent on temperature. It depends on whether or not a catalyst is present, and in gas-phase reactions, it might be a function of total pressure. Here, it will be assumed that Ka depends only on temperature. It was the great Swedish chemist Arrhenius who first suggested that the temperature dependence of the specific reaction rate, Ka, could be correlated by an equation of the type, and here we have the Arrhenius equations. K of A, dependent of temperature, is equal to capital A times the exponential of minus capital E divided by RT, where A is called the pre-exponential factor or frequency factor. Capital E is the activation energy, which could be in joules per mole or calorie per mole. R, the gas constant, that could be equal to 8.314 joules per mole Kelvin or 1.987 calories per mole Kelvin. And T is the absolute, capital T is the absolute temperature in Kelvin. Why is there an activation energy? We need an activation energy because the molecules need energy to distort or stretch their bonds so that they break them and thus form new bonds. And they need it too because the steric and electron repulsion forces must be overcome as the reactant molecules come too close together. The activation energy, capital A, is determined experimentally by carrying out the reaction at several different temperatures. After taking the natural log of Arrhenius equations, we obtain that the natural log of Ka is equal to the natural log of capital A minus capital E divided by the gas constant times 1 divided by capital T, which is the temperature. And we see that the activation energy can be found from a plot of the natural log of Ka has a function of 1 in T. So this is what we do in the lab. At different temperatures, we make the reaction and then we calculate the rate constant, and then we make a plot of the natural log of the rate constant against 1 in T, and we will see that the slope will be minus capital E divided by R, and the intersection with the vertical axis is natural log of the of the pre-exponential factor, capital A. The larger the activation energy, the more temperature sensitive is the rate of reaction. The Arrhenius equation, it can be put in a most useful form by finding the specific reaction rate at a temperature T0. This is K at T0 is equal to capital A exponential of minus capital E divided by RT0, and at temperature T, K of at temperature T is equal to the capital A of pre-exponential factor multiplied by the exponential of minus E capital divided by RT. So, if we take the ratio of these two equations, we will have that the rate constant at temperature T is equal to the rate constant at temperature T0 times the exponential of capital E divided by R times 1 divided by T0 minus 1 divided by T. So here we can see that we can calculate K at different temperatures if we have the value of K at a temperature T0. Stoichiometry. If the rate law depends on more than one species, we must relate the concentration of the different species to each other. This relationship is easily established with the aid of a stoichiometric table. This table presents the stoichiometric relationships between reactant molecules for a single reaction. These relationships will be developed for the general reaction, A of A plus B of B goes to C of C plus D of D. We must remember that the lowercase letters are the stoichiometric coefficients and the capital letters are the reactants or products. We must recall that we have already used stoichiometry to relate the relative rate of reaction for this reaction when we saw competency 2. Remember that we established that the rate of A divided by the stoichiometric coefficient of A is equal to the rate of B divided by the stoichiometric coefficient of B, and is equal to the rate of C divided by the stoichiometric coefficient of C, and is equal to the rate of D divided by the stoichiometric coefficient of D. And we must remember too that if A and B are disappearing, then we need to introduce the negative sign. And C and D are the products, so they are positive. In formulating our stoichiometric table, we shall take species A as our basis of calculation. In this case, species A will be the limiting reactant. In part 5 of this competency, we will develop the stoichiometric relationship for reactant species that give the change in the number of moles of each species, which are A, B, C, and D. And that's something that we will go through in the next part, in part 5 of this competency.